All right, now that we've looked a bit at just sort of the acid-base chemistry of amines, now we need to take a look at other reactions of amines. So pretty much in all cases, the lone pair on the nitrogen will be the place where reactions take place. We've already talked about how we can do simple acid-base chemistry. These are reversible reactions where we can make a conjugate acid. Along with them being quite basic, this also means they're going to be fairly nucleophilic. So this lone pair will be very reactive. We can use neutral amines to do alkylation reactions, where this is just going to be an SN2 reaction to displace things like alkyl bromides. And now we can make ammonium salts. We'll talk more about this on the next slide. And in the last section, we just saw how we can have nucleophilic amines attack acid chlorides, where these will go through tetrahedral intermediates, and then finally give amides as products after collapse of this tetrahedral intermediate and proton transfer. So let's take a closer look at these alkylation reactions. So this seems like an obvious way to make different types of alkylamines or amine derivatives. But this becomes a bit more complicated than you would expect. Because along with our single reaction, where we could have this ammonia do a substitution reaction, we end up with actually quite a few problems. So immediately after the reaction, we actually have a positive charge on the nitrogen with a bromide anion. But if we have more ammonia around in the reaction, it can also act as a base. So we're always going to be having these acid-base reactions where we could have, plus ammonia come in and deprotonate this, and we get out a primary amine. And so the problem with trying to get ammonia to react with an alkyl bromide is that this amine here actually becomes a little bit more reactive. This ends up being a bit more nucleophilic than just ammonia on its own. We saw this reflected in the pKa trend as well. So that means that this alkylamine can also react with an alkyl bromide. And after proton transfer, we would end up making now a secondary amine. Secondary amines can continue to react with ethyl bromide again to give tertiary amines. And tertiary amines potentially could keep on reacting to give fully substituted quaternary ammonium salts. Then these would have bromide counterions. Because of this equilibria, it's pretty hard to only get a single reaction between an amine and an alkyl bromide without having some of these over-alkylation problems. And so one of the big solutions that we're going to be talking about right now in this section is how can we make a primary amine efficiently? And how can we make things like secondary or tertiary amines selectively and control all the different groups as well? So the first method we're going to learn is called the Gabriel synthesis. And this is a solution to the primary amine problem. So we end up having a molecule. This is called phthalimide. So an imide is when you have a nitrogen with two carbonyls on either side. And what this will do is have this central nitrogen here act as an ammonia surrogate. Because we have these two carbonyls on either side of the nitrogen, they're going to take electron density away, and this NH bond becomes very, very acidic. So this pKa, I think, is around 9 or so. So something like potassium hydroxide can fully deprotonate it and really remove any of the phthalimide equilibrium. This new anion is quite nucleophilic, and it can be alkylated. Now we can only have it react once, because it will only react in its negatively charged form. It's not very, the neutral form on its own can't be deprotonated again, so it can't react again. So this is the first step of the Gabriel synthesis, will be alkylation of phthalimide. In the second step, we're going to have hydrazine which you guys have seen previously in the Wolff-Kishner reaction. This is a very nucleophilic amine, and this will be able to directly attack this imide. So imides are more reactive than your average amide. That's because amides are stabilized by the resonance from the nitrogen, and now this nitrogen is trying to share its electron donating ability to two different carbonyls, so the ethers become weakened. Along the way, we'll have this come down. We'd end up first having an addition reaction where hydrazine is attaching. You can imagine now collapse of this intermediate along with proton transfers. We're going to kick out the amide as the anion. We're going to make the amide now on the other side. And now we still have another very nucleophilic amine attached to the molecule, and it is 1, 2, 3, 4, 5, 6 atoms away from this carbonyl. So it'll also be able to attack intramolecularly. Normally amides are fairly resistant to nucleophilic attack, but since this is intramolecular, it helps quite a bit. And now, once again, we're going to have another proton transfer, collapse of the tetrahedral intermediate. And this gives us now a new heterocycle byproduct along with a simple primary amine. So in the day, if we have an alkyl bromide that we want to turn into a primary amine, we use phthalimide to displace it. The nitrogen of the phthalimide ends up serving as an ammonia surrogate. And then upon reaction with hydrazine, it's able to do 2 additions onto each of these carbonyls to excise the primary amine and have it form. So this is a good way to controllably singly introduce an NH2 group to an alkyl halide. In this next section, we're just going to go through actually a number of ways that we have seen before in order to make different types of nitrogen-containing groups and amines. So this is something we're all familiar with. This is just going to be the electrophilic aromatic substitution or nitration of benzene. Nitric acid, sulfuric acid can introduce a nitro group. And we have a number of ways that we've learned in order to reduce this nitro group to an aniline. Tin chloride was the one that was the most orthogonal and most practically useful. So this would be another way to now make a primary arylamine. There are some other options. This is probably my favorite way. If I were to actually do this in the lab, I really like this 2-step process. And that's using sodium azide as your nitrogen source. So sodium azide, we know, is going to be a very good nucleophile. We've seen this a number of times in the class. You could do this in something like DMSO, just to reinforce that this will be an SN2 process. And this can displace the alkyl halide. Nitrogen this is a great molecule to carry around as also a primary amine surrogate because it has this N2 group that's kind of built in, and there's a number of ways to remove this. If we want to remove this, you can actually use things like lithium aluminum hydride. another strong reducing agent will convert an azide to a primary amine, or with hydrogenolysis conditions, so using hydrogen gas and platinum oxide. This will also reduce an azide to a primary amine. So both of these are alternative ways. Of course, you want to watch out with something like lithium aluminum hydride because you could reduce esters, ketones, and a variety of other functional groups. Platinum and hydrogen is a little bit milder. You just want to be aware of whether or not you have a double bond in the molecule that could also be reduced.